All right, good morning, everyone. Welcome to the 2024 Summer Virtual Education for the Virginia Waterwell Association. We are starting the first course with our Brent Waters, the Senior Vice President of WSP Earth Environment. He will be bringing content related to the electric resistivity testing, imaging, and then some groundwater modeling. Brent Waters is a senior vice president and principal hydrogeologist with WSP, Earth and Environment, with over 35 years of experience in geologic, hydrogeologic, and geophysical consulting for water resource, mining, manufacturing, power, and oil and gas sector clients. Brent's main areas of expertise include characterization of fractured bedrock and karst aquifers for the purpose of groundwater exploration and development, mine dewatering and groundwater inflow seepage management, identification of contaminant flow pathways, and geotechnical and engineering geology related investigations. Other specialties include water resource planning, permitting of new water supplies, well design, aquifer testing, and evaluation of alternative water supplies, including quarry water storage, riverbank filtration, and horizontal collector wells, brackish groundwater supplies, and aquifer storage and recovery evaluations and design studies. Thank you, Brent, for providing us this education this morning. And you have the floor now.
Okay, thanks a lot, Christina. That was great. You read my entire profile. I wasn't expecting that. That was good enunciation on all those hydro-technical words. Okay, so I got 2 hours here to talk about Virginia groundwater, and got sort of a greatest hits collation here where I'd like to talk a little bit. Let's see if I can advance my slide. There you go. I'm going to briefly at the beginning of the presentation geek out a little bit on geology, hydrogeology, and talk about the physiographic geologic provinces in Virginia, a little bit about brief geologic history of Virginia. This, I think, helps in, might not help you drill a well better, but it might help you understand what you're drilling into, and nothing else, it might provide a little depth of geologic understanding of the state. Then we'll get into hydrogeology, occurrence and movement of groundwater, Virginia's groundwater resources, and then really the sort of my main topic and what I've spent my career in is groundwater exploration and water supply development, and we'll talk about fracture trace and fracture fabric analysis, electrical resistivity imaging, well development and construction. And we'll sort of summarize with a series of case studies, examples of some high yield well development, and then look at, managing and protecting our groundwater resources for future generations. Thank you. Okay. So there are 5 geologic provinces across the state, from east to west: Coastal Plain, Piedmont, Blue Ridge, Valley and Ridge, and a little bit of Appalachian Plateau. Most of West Virginia is in the Appalachian Plateau. We've got a huge variety of different types of geology across these physiographic provinces that we drill wells in and we get our groundwater from. So I thought it'd be important just to talk a little bit about each of the different provinces. And in sort of a broad sense, geologists like talking about how old things are. And, we're not talking about years, 40, 50 years. We're talking about billions of years, millions of years. So the youngest physiographic province and the youngest sediments geologically is the Coastal Plain on the east of 95, 0 to 140 million years old. The Piedmont, 200 to 1.2 billion years old, 200 million to 1.2 billion. The Blue Ridge is the oldest rocks in the state, generally 600 million to 1.1 billion. The valley and ridge is 300 to 600 million years typically, and the Allegheny Plateau's on the upper end of that, or the lower end of that. Coastal plain, I'm sure most of you understand that this is the part of the state where you have unconsolidated, up to 6,000 feet of unconsolidated aquifers and aquatards, confining units, mixed sand and sands, gravels, and clays, gently dipping to the southeast, and water wells in the coastal plain one have to be gravel packed, have to be mud rotary drilled, and because of intense use over the decades, century, requires withdrawal permits for protection of the resource. Piedmont province, probably one of the most difficult areas to find water in. Complex, moderately to very old igneous and metamorphic rocks, fractured rock only, open hole bedrock wells, typically yields from, quite often dry holes, low single digit gallons per minute up to and exceeding 400 gallons a minute. Blue Ridge province, similar to the Piedmont, maybe in some cases a little bit more difficult because the mountainous terrain, deep depth bedrock, or to groundwater, and just the hardness of the rock. Valley and ridge, typically it's folded Paleozoic sedimentary rocks, limestones and sandstones. The limestones can yield very high yields of 2,000 gallons a minute or greater, but have very difficult drilling, potentially difficult drilling conditions, and the karstic terrain, and the sandstones and the shales can have very low yield and very poor water quality. Some of the examples or photographs of the karst terrain, sinkholes in that upper left, a sinking creek or sinking stream, a cave system, and fall-in springs, a spring emerging out of the ground and then into a waterfall. Allegheny Plateau province, rocks or shales, sandstones, coal seams, flat lying, typical low yield, typical poor water quality, and at depth can be salty. This photograph sort of shows the main area of the bedrock well drilling provinces, the Blue Ridge, the Valley and Ridge, mostly the Shenandoah Valley there with Massanutten Mountain syncline in the middle, and then continued more Valley and Ridge and Appalachian Plateau to the west. So brief geologic history, I'll get into that over the next couple slides. We spans more than 1 billion years old. There's evidence of the breakup of 2 supercontinents, the ocean opening up of 2 oceans, and 3 periods of mountain building. And I am going to talk about this a little bit. It might bore some of you guys to tears, but I think it's sort of interesting in that it provides context to some of the rocks that you drill through. So the rock cycle, typically, the igneous rocks form when molten material cools and hardens, whether in the ground, in the subsurface, deep in the subsurface, miles underground, or at the surface through volcanic eruptions. When that igneous rock erodes and gets deposited through streams and rivers, deltas, and oceans, it forms through time, heat, burial. It will form sedimentary rocks, solidified, consolidated sedimentary rocks, and then if that material then is buried deeper and under extreme heat and pressure, will form metamorphic rock. And so that's sort of the cycle, the rock cycle. Some examples of igneous rocks, these pillow structures in the upper left, that's a basalt, that's the Catoctin greenstone that forms the Blue Ridge that many of us cross over. And the Catoctin is a basalt similar to what you would find in Hawaii that either on land or into the ocean was deposited. Volcanic rocks with the second picture in the middle, upper middle, is blast of those are bombs coming out of extruding out of a volcano. Obsidian on the far right, glass rapid cooled silica dioxide, pumice lower left, a volcanic tuff in the lower middle, and then on the lower right, that is that's up near Monterey. It's a core of a volcano that volcanoes did occur throughout the state millions of years ago, and this is a core of an old volcano that's preserved just south of Monterey. Igneous intrusive rocks through crystallization, solidification in the subsurface under heat actually form minerals, and you can see those minerals, coarse grained minerals, granite and diorite shown there in those photographs. Metamorphic rocks, schist, gneiss, slate, phyllite, different types of metamorphic rocks, depending on what the host rock was and the type of metamorphism that occurred to it. Sedimentary rocks, conglomerates, sand and gravels, typical in more high energy environments, cross bedding, sandstones in the lower left, again, high energy environments. The stack there of limestone, sedimentary rock layering, and then fossils, of course, common in many of the sedimentary rocks. The picture on the lower left that I have on my computer screen as well is the Valley of the 10 Peaks in Banff National Park, and that's where I did my master's thesis back in the early 80s, backpacking throughout the Canadian Rockies looking at carbonate sedimentology. Okay, so a continuation of the brief geologic history. We talked about a couple mountain building periods. The core of Virginia, of North America, is Grenville age, which is 1.1 to 1.3 billion years old. It was the continent, the North American continent at that period of time. It ended essentially at the Blue Ridge Mountains. Everything east of the Blue Ridge Mountains has been accreted or added through deposition onto North America. So all of that's extra land, so to speak, over the last 1.1 billion years. During late Precambrian, the Iapyan rifting, that is what formed the Catoctin basalts. I guess slide on that, and then 150 million years of passive margin deposition, quiet seas. We were around the equator at that point, so all the deposition was limestone, was carbonates, and that's the valley and ridge, the 10,000 feet or so of carbonate rocks deposited there in shales. And then the tectonic orogeny, mountain building, basically adding, accreting island arc provinces onto the North American Craton through the Acadian, and then finally with the Alleghanian in Permian time, where North America and Africa collided, and then shortly after that, it started all over again with Mid-Atlantic rifting and our modern passive margin. So you can see a series of rifting, separation, pulling apart, compression, mountain building multiple times, and then rifting, pulling apart, formation of the Mid-Atlantic Ridge and the Atlantic Ocean. I thought this slide was interesting. It basically shows the rift. Now we see the Mid-Atlantic Rift out in the middle of the Atlantic Ocean. Well, it's preserved. The older one, late Precambrian, is preserved right on the edge of the east coast and Gulf Coast of North America, and the continent, when it broke up at that point, a lot of basalt came flowing out either in sills or out on the ocean floor and formed the Catoctin Formation, which is now one of the most prevalent because of resistant weathering. It forms the Blue Ridge Mountain primarily, along with some of the quartzites above it. And then the Paleozoic, called the limestones, I already mentioned this, period of warm tropical seas on the east coast of North America. Shallow marine organisms flourished, and the deposition of limestone, 10,000 feet or so of it. During the big collision, and it's similar to what happened with India and Asia. Two continents collided and pushed and pushed and pushed together, forming very large mountains, the Himalayas. There's evidence that the Appalachians were as big as the Himalayas back in Permian time, 35,000 feet or so of relief. And so it just, it's pretty cool to think that of that geologic history of passive Caribbean-like seas for hundreds of millions of years, and then Himalayan mountains forming. And this is what the Himalayas look like today. This is what the Blue Ridge looks like today after erosion. So a couple 100 million years of erosion, and you end up with resistant rock forming the ridges, and everything else sort of peniplaned and flattened out. And then real old age would be equivalent to like the Canadian Shield, which has been weathering for a long time, a very stable Precambrian basement. Atlantic rifting, a lot of our drilling ends up being in this horrible soft red siltstone, shale, tan sandstones. Sometimes, like in the Culpeper Basin and some other areas, you can find good water, 100, 200 gallons a minute plus, but often it's dry holes or, single digit gallons per minute formed in these basins. When the continent broke apart, it was filled with lake deposits and shallow riverine deposits and whatnot, and was not solidified very hard. So it's a soft rock. It doesn't hold the fractures. And this picture is the basins, the Newark Culpeper Basin, Taylorsville Basin, Richmond Basin, etc. And some of the rocks, the border conglomerate on the edges of the basin, big alluvial fan deposits, and swarms of diabase dike intruding into the sedimentary rock with the chill zones on either side of it. And all these have implications to finding water, all the types of fractures, all the types of hardness of the rock, and etc. Make a difference when you're looking for water. That's why I'm going through a lot of this stuff. Mud, some of the red shales in the Triassic rock, mud crack, playa lake type deposits with dinosaur footprints and stuff. So it was a pretty cool period of time with dinosaurs crawling marching around these shallow lake deposits. And then the Atlantic coastal plain, 75 million years of sediment deposition, and subsidence sinking to allow that sediment to continue to form vertically on top of the igneous basement. Atlantic coastal plain, a little bit. I just want to show the state fossil. We do have a state fossil, and it's the scallop shell from 3 million years ago. Other photographs of some of the sand and gravel type deposits, soil formation above it. So there was, from I-95 back to Virginia Beach, the seas transgress, regress several times, and that's why you end up with sand and gravel deposits that look like river deposits, but they're on top of a terrace or top of a ridge. They were deposited a long time ago when the sea levels were up. And then of course shell beds, up in high elevations, 100 miles inland of where the ocean is now. One note is that this nice sequence of coastal plain sediments was impacted by an asteroid about 35 million years ago. It hit right basically at the end of the Chesapeake, maybe why the Chesapeake Bay entrance is where it is. It went right through all the coastal plain sediments at that time. It smashed into the underlying Piedmont crystalline rock and fractured it up and removed a ton of stuff and caused a tidal wave that topped up against the Blue Ridge Mountains. Pretty major event. Wouldn't want to go through it now, but it happened. And it took until the 1990s for us to understand that this event occurred through coring and a mix-up of the fossils, a flipping of the beds, just a lot of interesting stuff that probably confused geologists for a long period of time before they came up with the idea of an impact crater. So, okay. Now we're gonna switch a little bit to the hydrologic to groundwater occurrence and movement. So you got to start with the hydrologic cycle. The hydrologic cycle starts with evaporation off of surface water bodies and transpiration off of plants. That ET puts moisture into the atmosphere, where that moisture will condense and precipitate on the land surface through as precipitation, either rainfall, snow, or ice. That water, part of the hydrologic cycle, will run off the land surface into surface water bodies, eventually back to the ocean, or will infiltrate, percolate down through the soil and subsurface material to the groundwater table. And that is where all groundwater comes from. It comes from, well, yeah, that's essentially, that's where all groundwater comes from. It's from the rain. And it's been doing it for a long period of time, and it's filled up all the pores and cracks in the subsurface with nice fresh water. This basically shows what the water table is, where precipitation infiltrates. If it makes it past the root zone, which in the summertime none of it does, practically it all gets transpired up through the root zone. But in the wintertime, when there aren't leaves on the trees, it will get through the root zone more readily and will recharge the groundwater. So most of the recharge occurs from leaf off, end of October, probably through April, May, before, as the leaves start growing, as the greening up of the spring starts occurring again. So that's when all the recharge occurs. So if you have a dry winter, it's not a dry summer necessarily that hurts our water supply, our groundwater supply. That might hurt our surface water supplies, but it's the dry winters. And that is that, when you don't get snow melt or snowfall, slow infiltration of snow melt, etc., and just steady rains through good winter season, good spring season, that's when all the good recharge occurs. And that's what's recharges our water, our groundwater. And so when groundwater infiltrates through the subsurface, it's going to be flowing through pore spaces. And that pore space could be an unconsolidated material, basically in between grains of sand and gravel and silt. And so it will flow somewhat homogeneously through and uniformly through a unconsolidated material, where in most of the rest of the state, it's in fractured rock. It's gonna after it flows through the soil, saprolite, and gets down into the rock, it gets into secondary openings in the, the only porosity that rock typically has is the fractures, where the rock cracks up through stresses into joints and bed and plane fractures and whatnot. And that's where the water is going to flow. So you can imagine it's dependent on the orientation, the interconnectivity of the fractures, etc. So it can be unpredictable. It can be highly anisotropic and heterogeneous, and a little bit more difficult to predict how it's going to react. But in the bigger picture, it will essentially be homogeneous flow. It will connect up. The fractures do connect up. The types of aquifers. You can see the perched aquifer, shallow, when infiltrating water hits something that's a confining unit, hits something that's fine grained, prevents it from going any further, and it perches or sits on top of that. This is fairly common springtime, after heavy rains, impermeable layers, but typically they're not, they don't last through the summer months, that type of thing. Then beneath that is the permanent unconfined layer, the water table aquifer. That will be primarily the superficial aquifer, the shallow aquifer. As you go deeper, there's confining units, and you end up going into a confined aquifer. Most bedrock is a combination of unconfined and confined, due primarily to fracture connectivity. But you can see in this case, this unconsolidated, this aquifer system is recharged in the uplands, and it is under pressure beneath that confining unit, and will typically flow above the top of the aquifer, and in some cases flow above the ground surface as a flow-in artesian well. So time of travel, typically rainwater infiltrates, flows short distances, and discharges into nearby streams or springs, lakes, etc. And typically in the shallow, that shallow portion of the groundwater flow system is days or years. So that's why you can see increased stream flow after rainfall, not just from runoff, but from groundwater discharge a short period later. Especially near the groundwater divides, the water that travels vertically deeper into lower confined aquifers can take hundreds of years to finally come back and discharge to a discharge area. And in fact, age dating of the coastal plain aquifer system has shown that some of the water is up to 30 or 40,000 years old in some of the deeper parts of like the Potomac aquifer. So that's pretty amazing, you know, and it's still fresh, and it's still, you know, it's still traveling through there, but that's water that probably recharged up there near I-95 40,000 years ago. So pretty interesting. And all this rainwater, if the confining units are such that it does not flush fresh water through the aquifer system, then you'll end up with salt water. You'll end up with saline water that's probably depositional, you know, water that was there during the deposition of that material, the formation of that geologic formation, connate water, or from some past sea level high. Okay, so now we're going to start talking a little bit more about wells. Pumping when you pump put a pump in a well and pump it, it forms a drawdown cone or a cone of depression, essentially pulling water from storage, and that water gets replaced by water under hydraulic gradient radially towards that well, and ultimately forms a drawdown cone. In unconsolidated homogeneous aquifer system would be circular, and some other in fractured rock it could be elongated or along a fracture system. So it's not just a simple drawdown cone. It can be more complex, but the gist of it is that your drawdown will be the highest, the greatest, right in the well itself, and the aquifer and adjacent to the well. And the pictures, the photographs on the right, just showing that you know, the water may not be coming from right around the discharging well. In this case, it doesn't show the confining unit, but if you had a confining unit, then it might be coming from a up gradient recharge area. A little bit about fractures. Fractures mostly occur through stresses. In the picture in the upper left is a sort of a classic Appalachian compressional. When you have mountain building, you're pushing rocks together, you're folding them, and you form tension joints, strike joints, you form dip joints perpendicular or parallel to the compressional forces, and oblique joints that are usually shear. They're like 30 plus or minus 30 degrees from that compressional. That's where most water flows. So understanding joints and fractures and cracks in the rock are very important. I took a field trip back to my area up in Calgary, a geology field trip, not to look at the rocks that I studied 40 years ago, but to look at the cracks within the rocks. And it's pretty funny. We were doing a course on fractured network modeling and understanding groundwater flow and oil flow within the fractured networks. And so I got a free trip back to look at the cracks in the rocks. Pretty funny. Areas that you can see, along the outcrop in wintertime, you can see water in the form of ice seeping out of those fractures. Total groundwater withdrawals in Virginia, the big area here, the yellow, small groundwater withdrawal, relatively minor. This is the lower yield in Piedmont, primarily in the Allegheny Plateau, but this represents where most of the homeowners, the private wells, the smaller commercial, transient, non-transient type communities and establishments get their water from groundwater. It's what overwhelms this total groundwater withdrawal map are typically industry and agriculture. Up in the Shenandoah Valley, where you have limestone aquifers and you can produce wells that yield quite a bit of water, You get industry moving in. You also have agriculture, and same in the coastal plain where you can produce high yielding wells. Over on the eastern shore, it's for the chicken plants. In southeast, it's paper plants. It's a variety of different things. This sort of shows that the blue is the public water. Um, I think that may include also residential, but it's water supply, drinking water supply. The manufacturing shown is the next big component, followed by agriculture. I don't know why agriculture and irrigation are separate. I guess agriculture is food processing and whatnot, and then other smaller supplies for mining, commercial, etc. I mentioned earlier, east of 95, groundwater withdrawal permits are required. Due to overpumping of the coastal plain, the confined coastal plain aquifer. This is where the recharge water, the water that's in there, could be tens of thousands of years old. It's not being recharged fast enough. It's not a sustainable resource, so it has to be managed, and it's managed through a fairly complex groundwater flow model of the coastal plain, and looking at withdrawal, cone of depression type withdrawal impacts on other groundwater users near the withdrawal point. Okay, so that went faster than I thought. So I think this is where I'd like to take a break. Take a breather. I'm more than happy to take questions first, and then the break if there are any. If not, we can just take a 10-minute break.
Sure, if anyone has any questions, feel free to unmute yourself. I'll pause for about a minute, and then if no questions arise from the chat or online, I'll go ahead and start the break. All right, thank you. We'll be back in about 10 minutes or so.
Okay, thanks.
Okay, our break is coming to a close and we'll get started for the next portion of this course. And Brent, you can reshare now.
Okay. Yeah, hopefully everyone had a nice break. I think we're gonna move into some more pertinent and exciting aspects of the talk. Exploration and fractured bedrock, but I'm also going to be talking about well drilling techniques and pump testing and modeling, etc. So let's go to the next slide. Here's some outcrop views of what the challenge is when you're drilling in rock. You're trying to hit cracks. Now, there's a lot of cracks in this rock in particular, karstified cracks, but anybody that's been sitting up next to a quarry and looked at thousands of feet of quarry wall and only seen a couple areas of water seepage from a fracture knows that finding these types of fractures is like finding the proverbial needle in the haystack. Some of these cases, these are some pretty big karstified fractures. These would be productive aquifers if they were in the subsurface. Now here's some borehole videos, and so what you see on the top of the ground is what you see in the subsurface. Here, the well intersects a vertical fracture. Here, another two vertical fractures, karstified in this case. Same with that one. Now, if the well was a foot to the right, foot to the left, it would have missed this particular fracture. Might have hit another one, but it would have missed this one. And I think this was the main producer within the well. So a lot of it's luck, a lot of it's testing and skill. I think when you also bring in the fact that most bedrock wells aren't vertical, aren't plumb, and can veer off in different directions. Even when you locate a well on a fracture zone, you could be missing it at depth, 600 feet deep. Okay, so what do we do as geologists to help us find the proverbial needle in the haystack? There's a couple techniques that really have changed groundwater exploration. And the two primary ones are remote sensing, fracture trace or liniment analysis. And that's advanced with LiDAR and digital elevation modeling and shaded relief maps. And, in the past it was stereo pair aerial photographs and Landsat. And today it's drone taken LiDAR imagery that you go out on a property. I just at a property in Lynchburg a couple weeks ago, and our company flew a bunch of drones over and got very detailed photogrammetry and LiDAR and generated a LiDAR map that was 1 foot resolution for the entire 400-acre property in a very short period of time. So we're using stuff like that these days. The other one is geophysical imaging, and I say imaging. I've heard tomography used. I've heard of profiling and whatnot, but imaging, to me, you're generating an image of some sort of physical property in subsurface, and then trying to interpret that. In this case, we're interpreting it, trying to find groundwater flow. The other aspect of remote sensing analysis is matching that up with the actual geology that you see in the field to provide a level of confidence and confirmation that you're identifying the right fractures that you'll expect to see in the subsurface. And the image here, this is from Laitman and Perzak. Back in the 90s, I took a course from Perzak out of Penn State on fracture trace analysis. So you're at the field geologists out in the field collecting data, taking photogrammetry from air, drone, or satellite, and trying to map out these fracture zones that are surface manifestations at the surface, manifest themselves as linear depressions. And that's the whole philosophy about that. This is a map that I produced. I still use it. I produced this back in the 90s, doing a study up in Loudoun County, and it just stood out. These long linear features really stood out. That's the Blue Ridge Anticlinorium, and the Shenandoah River on the far left, and all hard Precambrian Grenville age basement granitic and gneissic rocks, and these lineaments can be traced for tens of miles, miles to 10 miles across. Pretty amazing. And then on a more detailed level, this is up against the Valley and Ridge Plateau and the Allegheny Plateau, doing a lineament analysis, fracture trace analysis. It's anyone can do this. I encourage well drillers to do this. There's a website that you can get shaded relief maps automatically on your internet browser, and look at a property. When you go to a property, look at it. You can also digitally get geologic maps. Look at that. This picture in the upper right, see that surface depression? I mean, that's just really classically shows where you have a more intense fracturing. You get deeper weathering, deeper soils, which provides more storage of water to recharge the groundwater, and you get more opportunities to intersect these fractures that are filled with water. And that you can tell by that, looking to the right or left of that fracture zone, you wouldn't yield much water, and you wouldn't have much groundwater flow if you were, let's say you're doing a contaminant investigation, trying to track where the contaminant plume's going. That's where it's going, and let's say you want to capture a contaminant plume. That's where you put your recovery well, or you want to dewater a quarry or a construction site. That's where you put your well. High yield wells is not just for water supply. High yield wells is for contaminant studies. It's for dewatering of construction sites. It's dewatering of mine sites. Understanding groundwater flow is understanding fractures, and it allows you to design engineering solutions for whatever your problem is, whatever the issue is that you're tackling. So the detailed geologic mapping, this is what we like doing. We don't get out too often, but when we do, we get out and we look at the outcrops, and we look at the orientation of the fractures and the spacing of the aperture width and the length and the intersections with other fractures. And we do these studies, and then we graphically summarize that through stereo nets and through rose diagrams. So here's a stereo net of a bunch of different fractures. You can see that the majority of fractures are northeast and east-west, west-northwest. And here's the Rose diagram of those fracture orientations. A easier way of understanding these fracture orientations. Well, here's the Rose diagram. Number C is the Rose diagram of the liniment analysis. So, what does that say to you? I mean, it says that the majority of your liniments, your topographic depressions, linear topographic depressions, match your fractures that you measure in the field. And therefore, you know that those liniments are really surface manifestations of underlying zones of increased fracture concentration, fracture traces. So pretty exciting stuff when you do this and you see it, and it just, at least here in the Appalachians, it fits. It makes sense because the compression of the orogenies that I talked about is from southeast to northwest. That's the compression. All your geologic formations strike perpendicular to that northeast. So, this fits the Appalachian geology. These fractures that we see in these rocks formed from the stresses that were put on these rocks over the last billion years. Hence the conversation that we had earlier. So integrating remote sensing and field geologic mapping allows you to develop a conceptual model of the fracture network and the fracture flow in the subsurface. This allows selection of favorable groundwater development areas over large regions. So that, let's say you're doing a county-wide study or study even on a 400-acre property or even a 30-acre property. You're going to know where you want to take your next level of study, and that's going to be your electrical resistivity imaging and your test well drilling. And it also, when you intersect wells, or where your well intersects fractures, these fracture zones, you're producing a more sustainable source. You're not hitting one fracture that is not a regional fracture, not interconnected with other fractures. You're hitting a swarm of fractures that are probably connected with a swarm of other fractures that are in different directions, etc. And like in this rock, this picture here, these subhorizontal bedding planes. So you get these vertical fractures, northeast, southwest, northwest, southeast, and you get horizontal bedding planes or foliations and whatnot that allow sort of vertical and horizontal movement in the groundwater. So you get sort of a sustainable or homogeneous flow within your bedrock aquifer, at least in these fracture zones. So, this data we use to generate groundwater favorability maps. Groundwater favorability map essentially is a bullseye map of where you should develop your groundwater. And so this is a geologic map of Augusta County showing well yields, showing the geology. We digitized everything, put the lineaments in, and then generated in ArcGIS a favorable raster map that's just like, what are the favorable features? Distance from fracture zones, distance from faults, types of formations, etc. There's like 8 or 9 things that we use. And this weighted raster map then basically says, okay, here are the areas that you should develop. You should take your study to the next level. This is one for Berkeley County, where we developed a series of groundwater exploration areas across the county. And then we started doing in selective ones. We ranked all of them. And then we started doing electrical resistivity imaging studying. We found some of the biggest wells. Robert Royal was out there drilling one with the airlift yield of 3,600 gallons a minute. I'm not saying that it was all because of this geologic analysis. I think most of it was because he could get his barber rig down into the fracture zones and open it up. But either way, that's the process of linking geology, remote sensing geology, and then identifying where you should go. This one here is a Woodstock area, and you can see these huge lineaments, and then the thrust faults and the stratigraphic formations. I mean, it's just a plethora of information. So the next step, for us at least, is geophysics. And geophysics, like I just mentioned, is a non-invasive way of measuring physical properties of the subsurface to infer what's going on in the subsurface. And we acquire the geophysical data typically to either plan view or profile view for two-dimensional applications. But if we collect enough of it, we can essentially image a three-dimensional space within the subsurface. And we can do it on land, on water, and in the subsurface. This picture is Papua New Guinea. This picture is Currituck Sound. And this picture is up in the Andes, in the high desert of Peru, I think. Different types of geophysical methods. Really, the only one we offer all the services for all these geophysical ones, but electrical resistivity imaging, the one I'm going to talk about here. And a little bit about us. We have a bunch of geophysicists. A lot of them are geologists that use geophysics, like me. And we own and maintain all our own equipment. And you can see the picture's a bit dated. I don't have any gray or anything. A bit skinnier back then. And there's Mac, my partner in crime. Okay, so back to how we use ERI for groundwater exploration. So here's the map of the fracture trace, and what we're looking for. That's the goal. Well, this is an example of what a fracture zone looks like in the outcrop. So obviously, if you hit the fracture zone, and it's only 50 foot wide or so, you're gonna generate water. Where if you miss it, you're not. So, and here's a electrical resistivity profile. This is in ohm meters. We laid out electric cable on the ground. We injected electricity. We measured how that electricity flowed through the ground. Then we used an inverse modeling program that imaged and produced an image of the subsurface electrical resistivity. So your high resistivities is where it's dry, basically. You don't have where your rock, you don't have any fractures in your rock, or your soil is above the water table, or it's rocky, it's sandy, whatever. And where it's low is where you have weathering, you have clay minerals, you have fracture zones with increased porosity, you have water. So this is, like water witching, we use this to find where the water is in the subsurface. And we use it, we do the fracture trace, we do the geologic map and fracture fabric analysis, and we know where we probably should be drilling, but then we use this to more precisely locate, confirm, and characterize dip and whatnot of the water-bearing fractures. Okay, this already went through some of this. Electrical resistivity is a measure of how easily electricity flows through a material. Primary properties include interconnected porosity, water saturation, pore water salinity, and clay mineral content. Increases in all of those things will lower the resistivity, increase conductivity, inverse. Pros of electrical resistivity imaging: super high density of data points, full coverage, good for mapping vertical features like fracture zones, also stratigraphy, depth to rock, karst, and groundwater pathways and quality. You can map out plumes, you can map out subtle features, etc. And cons: labor intensive, impacted by cultural noise, and you really, of course, need intrusive samples to confirm interpretations. You always need to put a hole in there. This picture here, we did a 3D survey over this sinkhole, or this covered sinkhole. And I stripped away all the resistivity except the low resistivity, and you can see that the throat of the sinkhole and the main sinkhole here, or maybe this is the sediment, the clay-filled sediment, and here's the throat of the karst pipe going down. So that's an example of using it for 3D. So this is an example of a fairly typical electrical resistivity profile. Some of the stuff I don't know, can't interpret, some can't guess until you drill holes and stuff. But what stands out is this middle feature where it's low resistivity with high resistivity on either side, and it's vertical, subvertical. And this is where you're going to find, higher than average yielding wells, big water. Blue-green indicative of low resistivity, clay or saturated soils, and high porosity in the bedrock. Orange and red indicative of resistive dry soil, low porosity, competent rock. Test wells should target the low resistivity zones. So that's where it can help. In this case, we didn't find anything. So no water. There's no indication at all of I think this low resistivity horizontal zone here is either a shale layer or it's weathered saprolite bedrock, and there's basically, we didn't find any water path fracture zones on this line. So that was a bust, but at least we know not to drill, so that's good. Here's some examples. WSP, Golder. I started with Golder 25 years ago. Biotite gneiss, metamorphic Piedmont, 250 gallons a minute. Granitic gneiss, 300 gallons a minute. Biotite gneiss, this one up in Caroline County. The water was salty. We couldn't use it, but for a Piedmont, it's a 1,100 gallon a minute well. Pretty amazing. Hornblende gneiss, 350. Limestone, lots of limestone wells over 1,000 gallons a minute. And up in Fauquier County in the horrible Triassic rock, 250 gallons a minute. A lot of dry holes though, also in the Triassic rock. So here's some borehole pictures of some of these wells. Again, the fractured nature of the what we intersected. That's what you're trying for. Open fractures where the water can flow. So let's talk a little bit about water supply well drilling methods. Most of you guys know these things, but for maybe the bedrock well drillers, you don't know much about mud rotary and vice versa. And then there's the dual rotary, and there's sonic. I'm not really going to talk about sonic, but that's used quite a bit in environmental primarily. But let's take a look at bedrock well construction. Bedrock is typically you are drilling with air hammer, air rotary with an air hammer bit. Your well casing will extend down into bedrock. You have to sometimes put superficial casing, sometimes have to drill mud rotary if it's thick enough coastal plain or weathered saprolite till you get to bedrock. But you oversize the drill, you put the casing in, you grout it up, and then you drill open hole and hope that you intersect fractures. Maximize open area, open screen maze. Okay, yep. And karst wells need a class 1, 100 feet of grouted casing. This is also the case if you have a class 2B Piedmont well or Blue Ridge well that is close to a contaminant source, potential source. So here's a picture of an air hammer bit, fast drilling speeds, relatively low cost, dual rotary casing advancement, top head drive for the drill string, and the bottom rotary table to advance the casing with carbide bit. I mentioned this because there a lot of the wells that we drill for large supplies for municipalities and industry are in karstic formations, and so we've successfully used dual rotary a lot in Virginia. Advantage of standard rotary. Here's a picture of the reamer and a stabilizer, another reamer. Trying to get a nice straight hole, faster, less expensive drilling. The disadvantages, sometimes uncertain final well construction due to potential need to telescope the well. This was very specifically for a presentation on drilling in karst. So some of these are a little bit slanted towards dual rotary, but you can see, and I've seen well construction like this where you've had to telescope the well multiple times every time you hit a karstic zone where you lose circulation. You have to seal it off and drill another, and then case it off and drill down through it, and you lose that water to the well. Reverse circulation is used a lot out west. It's used in coastal plain areas as well, due to the high you're using high upflow velocity. So in the reverse circulation, all your drill cuttings and fluids are sitting outside the drill string, and the pump pumps the material up the drill string. So because you have a smaller cross-sectional area, you increase the velocity inside the drill string, and that's what removes the cuttings. In reverse circulation wells that we've drilled in the coastal plain, I've seen boulders, head-sized boulders that come up through the drill string pipe. I mean, obviously using very large diameter drill string pipe, but very effective method, and a good way of producing a clean borehole wall, a clean, efficient well. Disadvantages: does not stabilize the borehole. You're not really using mud, and you don't have the mud weight to hold the hole open. So I mean, you can put mud in it, but for a high efficiency well, you shouldn't. Difficult to control large volumes of water. Less common drilling technique. Some of the drilling challenges in karst: pinnacled bedrock surfaces with deep voids and weather zones. So where do you set your surface casing? You might hit a ledge and you say, okay, this is where I set my surface casing, done. And then 10 feet later, 20 feet later, you're back into a complete mud-filled void. Then you have to pull your case and re-drill it, set it. So loss of circulation in voids. You hit a void, that your water, your cuttings, your air, all your energy goes out into the formation, doesn't come back up the hole. Your cuttings stay in the hole. Mud seams, where do you cut it off? Flooding of the bit. This is a problem in drilling elsewhere, but especially in karst, where you have very large, thousands of gallons a minute type flow. You can use foam, air relief sub, you can case off. There's a variety of ways that you can continue to drill even though you have too much water on your drill bit or on your air compressor. River gravel zones, difficult to deal with, crooked and deviated hole. So could break off the bit, may need to ream to get ream hole to get the casing in it. Okay, so dual rotary or the barber rig drilling methods. Casing advancement uses rotary table carbide bit, stabilizes the borehole, isolates difficult karst zones, you produce straight holes, allows better water management cuttings. Disadvantages, more expensive, and this is this is by manufacturers, a video on it from Foremost. I think I already showed this one, so that's a repeat. Okay, now let's take a look at drilling in the coastal plain. And this picture, it's horrible resolution. It's some ancient slide that I had, but it just shows that it's pretty variable in the coastal plain as well. Different depths to bedrock, different formations, different thicknesses, a variety of difficulties can be encountered in drilling in the coastal plain. It's not just layer cake. You need to understand your geology. You need to look at nearby well drill logs. That's the best information you can get. And so folks that have been drilling in the coastal plain basically know pretty much where to drill, but the USGS also has pretty detailed maps of where the aquifers are and the confining units are. With mud rotary, the mud is circulated down through the drill pipe and pushed out at the bottom of the drill bit, and the drill cuttings are removed as the mud rises in the annulus outside the drill string. And the drilling mud serves, it's the most important thing, is it serves to remove the cuttings, cool and lubricate the bit, build a filter cake on the borehole wall to prevent loss to the formation. So if you're continuing to lose water out into the formation, you won't be able to build a hole. You've got to plug up the annulus borehole wall with a filter cake, a mud filter cake, to prevent the borehole from collapsing in on itself, and control formation pressures, etc. Some of the things, kits, using a mud balance to see how heavy your mud is. It can get heavier. Sometimes you want it heavier. Sometimes if it's too light, you've got to be careful. So you can have additives to add to your mud. I was involved with a deep well in Newport News, reverse for a RO plant for Newport News, and the well driller made some mistakes on its mud and didn't manage the mud properly, and lost a bit and lost a casing, broke off casing. So it's very important. And of course, then the invasion of mud out into the aquifer, if you don't have a good filter cake, it's going to plug up your formation around the well that you may not be able to develop out later with developing techniques. The key mud properties: weight, viscosity, gel strength, and sand content. These are all different tools that you can use to monitor that as you go along. We already talked about reverse circulation. Okay, so that's a repeat. So gravel pack, even though this is shown in a natural pack, but a gravel pack, there's a lot of design considerations in a gravel pack well, and I'll go through a couple of those real quickly. What's your well constructed construction materials, the well depth, diameter, screen interval, slot size, and thickness and size of gravel pack. These are all considerations that you need to make when you're drilling. Carbon, steel, stainless steel, PVC, thick-walled PVC for RO or for brackish, or fiberglass reinforced plastic. These are all different well construction materials that you'll have to look at based on your local aquifer conditions. Well depth, again, that's usually determined by driller's knowledge or geophysical logging of the hole of the pilot hole after you drill the pilot hole. well diameter, expected yield of the well primarily, and sufficient to accommodate the pump, and sufficient to both reduce entrance and approach velocities and uphole velocities. All those things are pretty important in developing an efficient well. Screen interval typically by the geophysical log, determined by the geophysical log. You maximize your screen to reduce partial penetration, etc. So your filter pack should be 4 to 6 times coarser than the aquifer material, and it should be generally 3 to 6 inches thick. So I don't know if I have a slide on that, but your gravel filter pack will be designed based on sieve analyses of the formation that you're trying to screen off. And then your screen slot size selection will be designed based on the gravel pack that you've designed. So you try to retain 85 to 95% of your gravel pack. So you want to maximize your gravel pack slot size. You don't want to just default go with 10 slot, go with 40 slot, go with 60 slot, whatever you can do based on this gravel filter pack selection. And that's going to be based on your sieve analysis. So all very important things. Approach velocity is, as groundwater moves towards a well, the flow vectors converge, and if the velocity exceeds a critical limit, it may transport particles into the gravel pack and into the well screen, and it may cause turbulent flow. So your approach velocity, that's the outside the borehole, at the borehole wall, should be less than 0.5 feet per second. If the value exceeds 0.1 foot per second, it may cause turbulent flow and well losses. The entrance velocity is more important. It should never exceed 0.1 feet per second. That will cause turbulent flow and will decrease the efficiency of the well and increase your pumping costs over the long term. The turbulent flow will promote release of gases, which could cause precipitation of minerals, including calcium carbonate and hematite, etc., and increases mechanical plugging, increases corrosive attack. So designing your gravel pack well is very important. Well efficiency is very important. And can be estimated from step drawdown tests or constant rate tests, distance drawdown analysis. And it's basically well efficiency is determined by the theoretical drawdown based on the transitivity of the aquifer, what the aquifer should draw down under a certain at a certain pumping rate, divided by the actual drawdown. So in some cases, your actual drawdown here, you can see your aquifer drawdown is here, your actual drawdown is here. And so that's the inefficiency, that's the head loss caused by moving through gravel pack and through the filter or the well screen, and then up the hole. I suspect most people on the call are not coastal plain well drillers or alluvial well drillers, so I'm trying to move through this pretty quick. Okay, so well development techniques, there's raw hiding or over pumping, mechanical surging, surge block, swabbing, air surging and pumping, high velocity, air water jetting using polyphosphates. And there's other techniques, hydropulse, even hydrofracking, in rock wells. Not really a development technique, but it is basically a development technique in that it increases the yield of the well. The whole purpose of well development is to make the well more efficient, thereby increasing the yield. So here's the original step test on this well. And then after additional well development, it increased substantially to those steps after development. That's just an improvement of the well efficiency. It doesn't change what the water level in the aquifer is. It only changes what the water level in the well is, which is mostly dependent on well efficiency. And so here's the curve analysis from the step drawdown test of before development and after development. You can see lower slope, lower drawdown, higher specific capacity. Okay. I think I mentioned all those points, and I think I mentioned this is a sort of a repeat. I didn't know I had that other slide. Mechanical, acid, biocide treatment, cleaning and wetting agents, surfactants, high velocity jetting. High velocity jetting, primarily for gravel pack wells should be used. Sonar jetting, impulse generation like hydropulse. So it's basically mini explosions with nitrogen gas. We use that a lot. And well freezing, aquafreed, I think it's called. Mixed reaction on that. And then, of course, add to this would be the fracking, essentially. Okay, so let's talk about some of using these techniques, some of the successes, high yield experiences that we've had in Virginia. Been working for the city of Salem, city of Roanoke, and Roanoke County since late 90s. At least with the city of Salem, and here's some of the wells that we've developed for them, totaling a capacity of nearly 15 million gallons a day. You can see a lot of the wells are over 1,000 gallons a minute, and have pretty decent specific capacities. Many, not all, but many are not surface influence and did not require any treatment at low turbidity. Could be pumped right into the system with disinfection. Others had to be treated either with microfiltration or with the surface water treatment plant like at Salem. So fun career, and still working with both, with Western Virginia and with City of Salem. Town of Dayton. This is a series of slides. We worked with them back in the late 90s and developed wells 1 and 2 that supplied their town and the turkey plant in their town, and they needed more water to add additional shifts to the turkey factory, whatnot. Oh, and because they were going off the Silver Lake spring, and so we went back out and we developed 2 additional wells that doubled their yield. The highest yield was 1,350 gallons a minute with only 24 feet of drawdown. And this is a pretty interesting, I think, Joel Maynard gave a talk a couple years ago about this. He was out there. He was all excited about it. He was out there with me and did some geophysical logging of the hole afterwards and stuff. And he gave a presentation to the Water Well Association a couple years ago. There's the location of the well. And see well 4, this is the 1,300 gallon a minute well, and that little blue dot right there is the main source of water for Silver Lake, which is, fishing. I think they stock it. I think trout fishing, and was the town Dayton's original water supply years ago, but it was deemed surface influence. So we developed wells 1 and 2 and a microfiltration plant. wait a minute, 1, 2, and yeah, 1 and 2, these two, and then came back and developed 3 and 4. So here's a series of pictures, I think. Okay, I think that's the picture that we just showed. This is Silver Lake. This is drilling. We built, we didn't want to drill right here. This was like the worst case scenario, but this is where the geophysics was the best. And we didn't want to impact the spring. We didn't want any turbidity to get into Silver Lake. It was springtime. It was high water, high rain, um, trout fishing season, and we didn't want anything to do with it, but we did. And we worked with the Mennonite farmers. These guys were fantastic, owners of this farm and this property. And so, what did we do to prepare? First of all, we built a platform to drill on to prevent from, basically built a big platform to prevent the rig from sinking in a sinkhole. And then, what are we going to do with all the water? So here's a series of pumps, pump into irrigation, and then irrigating alfalfa, I think, or soy. Get, but that's how we got rid of the well water, and as we started our drilling. But pretty soon the ground was saturated, so we had to build a pipeline to get it up over all the water up over the ridge top into a completely different drainage area. 1,500 feet, different watershed, using big pumps, using big silt bags, and those got blown out pretty quickly. Series of silt fences, and then all this as a filter for our turbid water. So here we are, we're airlifting 3,200 gallons a minute, 3,000 gallons a minute, right next to a spring. The lake did not get turbid from the air, from all the drilling. The spring wasn't impacted at all. All the water, it wasn't connected. It's amazing. And all the water was pumped up over and properly filtered through other farm fields. That's pretty cool. And then that stream that we were putting the water in eventually made it back around, and this is we had good clean surface water for the cows to hang out in, and so thank goodness. Another project, again, we used a series of geophysics, but this one sort of cheating, because this was at the Miller Course facility in what they call the Elkton Aquifer. It's up against the Blue Ridge, and there's 100 feet of soil, alluvium, karstic material, bedrock that, all the overlying colluvium provides a good filter. And so the water generally is low turbidity, not surface influenced, and the karstic aquifer from the acid rain runoff of the Blue Ridge, the ancestral Blue Ridge, which is as high as the Himalayas, produce this huge, thick karstic aquifer capped with a protective sediment filter. So pretty cool. The well was 2,400 gallons a minute. You can see that we built, and this was Robert Royal and Sid Noor did a fantastic, very professional job. Came in and built a big platform, brought out all the equipment, we built a large storage reservoir and then developed sort of a passive meandering path through fields for the water to release its turbidity prior to intersecting a trout stream just downstream. And we pump tested it for 30 days. It's not surface influence. Turbidity was 0.3 NTUs, had a decent specific capacity of 28 gallons a minute per foot, and was constructed all of stainless steel, food grade material. There's the reservoir, the initial reservoir, basically. There's one of the running the pump test. We had, I think, two pipelines going. I think this was on the beginning test. I think later we ran it into the system. Yeah, it was amazing amount of water, very productive aquifer, and excellent drilling accomplished it. It's really good. For Caroline County, some of the pictures from various wells, in addition to that 1,140 gallon a minute well that had the poor water quality, we've located several 380 gallon a minute wells, and several others, several over 100 gallons a minute. So we're helping them supply water for the growth along I-95. Louisa County up by Zion's Crossroads. It's an interesting story. The area right around Zion Crossroads that they wanted to grow, that interchange, develop hotels and develop subdivision, develop medical buildings, etc. There was no water. It was Piedmont, peelite, phyllite, schist. And we did locate two wells that were 30 gallons a minute. We did a lot of studies all around the Zion Crossroads area. And, like I said, we had two wells that were 30, 40 gallons a minute, but wasn't enough. So there was, years ago, there was a 200-acre piece of property shown there on the right that was purchased by the state as a prison. And ultimately the prison got turned down. The locals developed the Green Springs Historic Preservation Area to combat, having a prison developed there. So there was this 200-acre piece of property that came up for sale. The county bought it, and 50 acres, and the developer bought the other 150 acres. So they said, okay, go to town. You've got 200 acres to find water. So we did a bunch of geophysics and test well drilling, and you can see wells, some not so good, 43 and 65 gallons a minute, but there are, 175, 250, 350 gallons a minute. Found some really nice wells out in the Piedmont, using fracture trace geophysics, etc. And because of this was a huge, beautiful well field with 200 acres of protected land around it, ample recharge, etc. But there was a lot of protest, and there was a lawsuit about water rights because we were using this back down for water down at Zion's Crossroads. So we did pumped all the wells at the same time for 5 straight days and recovery, and did that hydrologic testing, and then we did constructed a groundwater flow model, all to determine what the sustainable yield of the aquifer was that would not impact folks. So this is sort of a schematic of what we were trying to do. It was over the, I missed one point there where geology matters. the boundary of the Green Springs Plutons right here on this lower left corner of this property. Everything else around the Green Springs Pluton is the schist, the phyllite, the rock that we couldn't find water in. This was a hornblende granitoid, like a diorite, granodiorite gneiss. It was very good rock for developing wells. It holds the fracture open. It was the optimal place to locate water. So it was called the Green Springs Pluton, and we did the drawdown test, or we did several wells and the drawdown test. And this is sort of a conceptual of potential impact on neighboring springs, streams, wetlands, and homes. This is the groundwater model. Here's the property, Green Springs well field. And the groundwater modeling, you discretize an entire watershed, surface watershed, equivalent to a groundwater watershed around your area of interest that you want to study. And use mathematical equations in a new computer model to calculate groundwater flow vectors and velocities out of each one of these cells. And then it combines it all, is interlinked, it combines, and you put in streams, you put in intermittent drainage areas, you put in a variety of different things to model natural behavior of surface water, groundwater. This is what the model looked like, had boundaries for the streams and tributaries, had no flow zones around the groundwater divide. And then of course vertically it was, had the saprolite and then 3 layers for the bedrock. And ultimately, we use this for the sustainable management of this well field. This shows the predicted steady state long-term drawdown of the well field. And I didn't mention, we put in 12 wells. We had 18 wells total, 12 monitoring wells around the entire property, and monitor those with data loggers for the full time. We monitor street flow and levels and wetlands, etc. So the groundwater model allowed us to look at sustainable development, and it showed that it receives ample recharge. It can sustain the full permitted withdrawal of the well field with minor drawdown impacts. There will be local decreases to groundwater discharge locally to the streams, but the wastewater used by that water is discharged just further downstream within the same watershed. And then, ever since then, since 2005, when we did this testing, we've been measuring groundwater flow. And this is, groundwater levels. And this is the groundwater levels. Now, this post-drought, and you can see that the water levels are mostly stable. Some drawdown in these wells here. These are monitoring wells closer to some of the main production wells, but we only had 3 of the 6 production wells online. They have now, or at least about to have now, all 6 online. So I suspect that will be reduced, but pretty interesting. We present this data to the Board of Supervisors and to the public in Louisa County on occasion. But this is the depth of the well here. So mostly the wells are 500-600 feet deep. And I think that is it. This just shows particle traces that you can do from the model to see how groundwater flows and how long it takes to flow through the model, which can be interesting. But the key here, I don't have a picture of it, I should have, but if you put the particles around your pumping well, you can reverse track them through time to their recharge area and come up and delineate the wellhead protection areas around each water supply well. So then you know what the area around your well that you shouldn't have contaminant sources in. So I think that is it. I hope you guys enjoyed it. And I am more than happy to answer questions.
Thank you, Brent.
There are
Feel
any.
free to unmute yourself, or if you want to send a question through the chat, I'll read it out to Brent. Brent, what you were just explaining, what kind of particulates or what kind of particles do you add to the monitoring wells around so you can see it leach back? What does
So
that look
yeah,
like?
I'm glad to explain that. I do that in the model itself. So in the cell that I have a pumping well, I will put particles around that well and then track how where the water okay. So the model is trying to predict how groundwater flows in the subsurface, and the particles will show you how it will flow in the subsurface, what the velocity is and stuff. So we're not actually physically putting particles in the ground. So it's just in the numeric model itself, to better understand what the contributing recharge areas for a well is.
And the additional 12 monitoring wells for this last project with Louisa County, that they were installed for the pure purpose of the pumping of those for the 5
Yeah.
days to see how it influences the surrounding area.
Yeah, they pulled all the stops out. They wanted to understand what the sustainability of this pumping of this well field was, and they want to make sure they weren't impacting neighbors. And so on their dime and our supervision, we put in 12 observation wells around the entire 200-acre property. And then we monitor those we've been monitoring those wells for the last 20 years, since 2005. And during the 5-day test, we're monitoring them continuously and then analyzing that data to determine aquifer properties, properties of flow within the bedrock, and to calibrate the groundwater flow model.
And that's all mainly due because they were under a lawsuit.
Yes.
Okay.
But I think it's fair to say that the more you understand your resource, where the water comes from, how much you've got, the better you will be at managing and protecting that resource.
I see we did have a few unmute themselves. Feel free to ask a question if you like.
I have a quick question. Brent, thank you for your presentation. It's very nice and very informative. I want to take you back into your presentation, and you talked about groundwater being saline in some areas. And you had mentioned some of it was because that was water trapped in the formation from seawater or deposits there in the rock formation. It takes me now to the part of the presentation of the Caroline County well at the Bowling Green exit that produced 1,100 gallons per minute. Do you know of any locality that has taken these saline wells and blended them with their public supply and monitored the saline level of the, say, subject 1,100 gallon per minute well? That allowed for flushing out of the brackishness of the well, and it became more usable at a higher flow rate as time progressed?
I do have not heard that. Caroline County is blending that well at 100 gallons a minute into their existing water supply, so that they can still keep the TDS, total dissolved solids, at a low enough level. I don't think the 100 gallons a minute is sufficient to stress or to flush out the water, but I suspect if it has not been flushed out over the last millions years, um, it's probably in an isolated fracture network, obviously fairly large, with a fair amount of storage, to produce 1,100 gallons a minute on a 48-hour pumping test with no evidence at all that it was running dry. So it's a very productive fracture network, but I think it's closed and isolated, and I don't think you'd ever be able to flush it out. I think the only thing you could do with that well, if you wanted to fully utilize it as a resource, as a full supply, is to get a reverse osmosis treatment system, membrane treatment. But you could. It's expensive, but you can.
But do they monitor that well over the last 10 years or so for the TDH level?
Yeah, and I haven't asked them what it is. I know when they were pumping it, it increased initially. I don't know where it's at now though. I haven't asked them about that. It's a good question. I'll have to ask them.
Thank you. Appreciate your time.
Yeah. And it's interesting because in pockets throughout Hanover and Caroline County, there are these salt, brinish, especially in some of the Triassic rocks, and I can see that because the Triassic rocks, one, they have gypsum in it, and that can produce the high TDS, the salt, but also they're shaly, and I can see pockets of water that just isn't connected with the water around it. But it's an unknown to me, and I'd like to understand it better. These saltwater deposits, saltwater areas within the Piedmont along I-95.
I've got Jesse and Gary also unmuted. Did either one of y'all have a question? I do have one on the chat.
Yeah, no, I was just going to say fascinating talk. Really enjoyed it.
Thanks, Jesse.
Brent, so
yeah.
Thank you, Jesse. Gary, did you want to ask anything?
Good
Okay.
to see you, Gary.
One question from the chat. What is the recommended method for getting a representative formation sample while mud rotary drilling?
Typically, you get your samples by drilling a pilot hole. Then later you ream it out for your well. And the reason why you do the smaller diameter hole is that it has more uphole velocity. You want to get a representative sample, so you want to be able to pump, stop drilling, clean out the hole, clean out the other material that might have fallen into it, and then drill 2 feet in or whatnot, and try to get that sediment up and capture that sediment in your mud pit, and try to capture all of it, including the fines. I think that's probably your best way, just taking care that you're getting a representative sample of the sediment at that exact zone, several hundred feet in the subsurface. It's hard. It's hard. I don't think there's other ways that are economical. Split spoon sample, that type of thing. You can do that too, but that's pretty expensive. The cabling and the tooling and whatnot you would need to stop drilling and put a split spoon down in a hole. You would for geotech, but for water supply wells that are hundreds of feet deep, you wouldn't.
Thank you. Any more questions? The last one that I just wanted to summarize, Brent, is it sounds like this technology could be utilized for, say, potentially some of the clients that maybe have agricultural needs or high-end, large scopes of land.
Yeah.
And then obviously your municipalities or industrial use.
Yeah, all of those, but we do it quite often just for homeowners on that are trying to develop even single lot wells in bad areas that if you have a 30 lot subdivision or even a 12 lot subdivision, you can run out a couple geophysical lines that may help find water for you. And the higher supply clients are the ones that we typically work for, but we do work quite often with residential developments and for irrigation at malls. I mean, irrigation, water bills are so high, so that's another area that, you might be able to use these technologies.
And so once the testing and imaging has been complete, you essentially provide the driller with the information and recommended well locations for them to set up on, and then it's up to them and the client to determine which well location that y'all determine on based on your testing and imaging to which one to try first, or you give a recommendation on the first one, second one, so on.
Typically, we depending on the size of the area, our costs are about $5,000 to $7,500 a day, inclusive of MOB and prep and demob and data analysis and reporting and staking. And we can cover, a 10, 20, 30 acre property in a day, maybe two. A 30, 40, 50 acre property in 2 or 3, that type of thing. It's not a high cost. And then what we produce is a table of anywhere from a couple to 6, 10, whatever, well locations that we recommend based on the fraction trace and the geophysics and our knowledge of the geology and coordinates for them, and go out and stake them in the field, and we rank them from first to whatever, first to 10th, first to 5th, and then the owner and the driller can decide how they want to proceed.
Thank you. Robert, did you have any other questions?
I'd like just add real quickly to Brent's comments. Mark McClellan asked about sampling in the coastal plain, and I would just point him and the group toward DEQs.
Yeah.
When you're going out and drilling a permitted well, they actually come out and monitor the drilling of the well. And they have some criteria they ask you to set your job up with. One of them is they require a T-head 18 to 24 inches above ground surface when you drill the 7 7/8 pilot hole. That's made out of 8-inch PVC. They monitor your mud quality, and they station one of their associates there at the back of your rig and actually put their hands into the discharge stream of that T-head. And then they get you to circulate the hole and then drill 10 feet at a fairly quick rate. And then at 10 foot, you stop. And they would get a sample of cuttings that come up, and they can actually get a repetition or a cadence of time, and they will capture those cuttings and then the cuttings will go away. And they'll get you the drill, typically the second 10-foot section of a 20-foot drill rod, and they'll capture those cuttings, a sample of them. And they repeat that each rod. And of course, the deeper you go, the longer duration each rod takes. But that gives them the ability to circulate, clean the hole, drill 10 foot, wait on the cuttings to appear at ground surface, collect a sample, then the cuttings stop coming and you drill the next 10-foot section. So I just want to add that, and that's something that could reach out to DEQ, Scott Bruce and his team, and get more details on that if it's necessary. Thank you.
Yeah, that's a good point. Great resource. And they're a great resource, you know, Brad White and Joel Maynard, great resource for the Valley and the Piedmont Blue Ridge. So, you know, if you, and they, especially Brad, he's more than happy to come out and geophysical log your well for free. And so, you know, use those resources. You know, maybe go through Scott, but I'm sure, you know, calling Brad White up directly if you have information. He's done a lot of work research on well yields and well drilling in the Blue Ridge.
Thank you, Brent. Thank you everyone for joining us this morning. This does conclude the first course. Greatly appreciate it, Brent. Hope
Thank
you'll
you.
join us again in the future. Great education. Learned a lot myself. And I'll see everyone next Thursday, 8 a.m. for the pump basics and advanced stray voltage. Y'all have a good week.
Thank you guys very much.